Okay, we're going to go through all of summer 2020. We're going to start with question 2 because question 1 is a small proportion question, and those are kind of rough. So I want to start with something easy. This is some advice that you guys should take when you're taking the exam for yourself. Is start with something easy. Don't start with small proportion. Or if you feel like starting with small proportion just because you want to get it out of the way, go ahead. But I'm not that kind of person. I want to start with the easy stuff first. So this first question has something to do with walls on. I don't know if it's like Walmart or playing on Walmart. I don't know what is walls on. Walls on. Oh, okay. Maybe it's a real thing. I have no idea. But it sounds like Walmart, but whatever the case is. We just got some company wants to change its inventory management and delivery system. Oh, it's like Amazon and Walmart. I just got it. It's Walmart and Amazon. Okay. Walzon's not a real place. Walmart is Walmart and Amazon. Okay, now I get it. Wants to test the null hypothesis that mean delivery time is at least 36 or 37 hours. So I'm just going to go ahead and write that down. Mu, or H null rather, H null colon mu is equal to 37 hours. Sorry, I shouldn't say equal to. It says at least 37 hours. So make sure that's a greater than or equal to 37. Against the alternative, we'll say H alternative colon mu is less than 37 hours. Assume delivery times are approximately normal. So that's always a fun factoid. Not make sure you write down approximately normal with a known standard deviation of 8 hours. And a random sample of 64 observations will be used to conduct the test. Before we start doing any calculations, one of the first few questions we get out of the way is what's the population, what's the distribution we're going to use. So first things first is this is the population is about it's about a mean because we're asking about delivery time, the answer to which is a number. So it's about a mean. Question is about a mean. And we were also told the distribution was approximately normal. So the population is normal as opposed to general. We use a general population or an arbitrary population when we don't know that the population is approximately normal. If it's not stated somewhere in the question, the population is approximately normal. Because it's approximately normal, and because we have the standard deviation is known, the population standard deviation is known, we will be using the z distribution, aka we will say that the value x bar minus mu over standard deviation sigma over square root of n is distributed normal 0, 1. So these are like little theoretical factoids we have to get out of the way before we actually do any calculations. But now that we've got that out of the way, we can move on to the next question. I guess it's not. I guess this is really all this is encompassed in question 1. So this is all question 1. Wants to know what the population is, what's the sampling distribution, is it exact or approximate? I assume that it's exact. What's confusing is that she says approximately normally distributed, but we're going to use the exact distribution of normal. I would assume, like, I should probably toggle back over, but for now, I'm assuming it's exact, even though it says approximately normal. I'll go back and change that if I need to. But let's move on to number 2. We've got Walzon decides to use the critical value of 35 in the hypothesis test. So they tell us the critical value right off the bat is 35. That means our rejection region looks like this. RR equals open set brace. We have to ask ourselves, is it going to be x bar less than something? I don't know why I'm writing the word x bar. I can just type or draw it x bar. X bar is either less than something or greater than something, depending on the tail of the test, or it's, you know, both if it's a two-tailed test. But in this case, it's a left-tailed test. We see that in the alternate hypothesis, we have a less than symbol. So this is a left-tailed test. So with that in mind, we'll have x bar is less than our critical value of 35. And we want to figure out what is the probability of rejecting the null given mu equals 37. As a reminder, I'm going to go to typing now. As a reminder, rejection is being inside the rejection region. So what does it mean to be inside the rejection region? It means that x bar is less than 35 given mu is 37. Of course, we need to convert this to z. So what I'm going to do is I'm going to use my handy dandy z-score formula and say this is p of 35 minus 37. I'll change this to z rather. This is z less than. Now the 35 we're going to deal with is 35 minus 37 over standard deviation was given to be 8 over our sample size, square root of our sample size of 64. Square root of 64. This comes out to be probability of z being less than -2. I'm going to go grab my calculator, do normal CDF. Normal CDF from -100 to -2 gives me 0.02. We'll go to 4 decimal places. 0.0228. That's the probability of rejecting if mu is 34. We've got a follow-up question. what's the probability of acceptance? So this is the next question. Number 3 is, what's the probability of accepting the null hypothesis? Pay close attention this time. Accepting. What's the opposite of rejection? Acceptance. Accepting, given the null hypothesis this time is 34. So I'm going to type one more time. If rejecting the null hypothesis was probability x bar was less than 35, then accepting is when x bar is greater than 35, and this time we're using mu equals 34. Once more, we need to convert this to a z-score. So I'm now going to go back and write probability of z is greater than 35 minus my mu now, which is 34. 34 over 8 over square root of 64. Notice that my value of mu has changed from problem 2 to problem 3. The value of mu in problem 2 was 37. It was given to be 37. So we used 37 to go figure out that z-score. But this time, mu is, I should probably let that continue. Mu is 34. So I'm using 34 here, okay? This is going to give me, I think, probability z is greater than 1, which comes out to be, if I had to guess, 0.1587. I feel like I know my z-scores well enough to know this z-score result. Normal CDF 1 to 100 is indeed 0.1587. Okay. Now it says to graphically depict the test. Again, this is not something that she's written the exam for summer 2020 as though it was administered with a blue book. We can't draw for our exam because it's being online. So being administered online. So we're going to just see what kind of question. Let's see, how does she ask this question? I'm going to revisit kind of what we did in the practice session 3, where I will clear this mess. Let's get rid of a lot of this. We're just going to be asked, realistically, we're going to have 2 bell curves. There's our mu is it greater than? At least. So actually, I'm going to save this for, let's move this to the right. Boop. And then the alternate is that it's less than 37. I tend to use red for my alternative. You don't have to, it doesn't really matter. And we've got our axis. This is the null hypothesis, where the mu value is 35. And this is our H alternative. I'm not sure which one they want us to use. They want us to use a certain value. Yes. Oh, actually, no, sorry. 35 is not the value they want us to use. I just assumed it was 35. Oh, right. Our null hypothesis was 37. All right, my mistake. 37 was the magic number. 35 was the critical value. That's what that was. Let's erase this. Undo. Okay. I probably could keep those things. Redo. Okay. And we'll put alternate here. 34 goes here, and 37 goes here. Of course, you're probably not going to have to draw this. What will probably be presented to you is a graph that looks like this. We've got a critical value. They might not even say 37 and 34. They might just say mu null and mu alpha, or alternative, I should say. So you might see that. And then what's going to be presented to you is, oh, let's do this in orange. We'll have a half line going this way, a parentheses, an interval going this way, marked right at the null hypothesis value. And then we'll also have the same thing going on for the critical value. And all your job is to label each of these things accordingly. So I'm going to type this. This half line is values in the null hypothesis, something like that. Or if I were to be wordier, values that satisfy the null hypothesis, or null hypothesis is true. All these sorts of things where we're saying that these are values that are in the null hypothesis. Conversely, we have this open interval is values in the alternate hypothesis, so values in the HA. What about the second intervals down below? This would be the rejection, or sorry, this is the acceptance region. And over here is the rejection region. Why is it the rejection region over here this time? If you watched the practice session 3, I have this kind of flipped. And same thing for the values, for the names of these things above. Why do they have these flipped? Well, this time it's a right-tailed test, or sorry, a left-tailed test. I'm going to get my left and right mixed up. If you recall, we were told, let's do this in green, H null was mu greater than or equal to 37, And the alternative was that mean delivery time was less than 37 hours. So this is a left-tailed test. So with that in mind, our rejection region is on the left. Values that are in the alternative hypothesis are on the left. And now we have to get into shading areas. So I'm going to try and, what should I do? Let's make this really large tool to shade, or should I just use a bucket tool? Bucket tool is kind of annoying because I have to section things off. So let's do this. Let's make this keep going all the way down like that. Let's make this guy go all the way down like this. Let's make the green line go all the way down like this. Okay. So we're going to be asked about a couple of shaded regions. Where's my bucket tool? We'll do this guy. We'll be asked about that. We'll be asked about this. And then we'll be asked about a couple other areas as well. So you'll be asked what is, let's not do that, that's a really hard to read color. What is area 1? What is area 2? What is area 3? And what is area 4? And what are these areas? Let's start by labeling the first two areas. I'm going to call this guy here area 1. This will be area 2. We don't see area 3 because if we tried to shade it, it would kind of overlap part of area 1. And if we tried to shade area 4, it would overlap area 2. But this up here is area 3. And this over here is area 4. Area 1, and again, you can reference the cheat sheet for this. I haven't been referencing my cheat sheet quite enough. But for drawing, this is on the page about 1 mean. It says, for drawing, area under the H null curve and inside the rejection region is alpha. So area 1 just so happens to be inside the rejection region, right? We highlighted it earlier. This was the rejection region. And this curve is the null hypothesis curve. So this is area under the null hypothesis curve and inside the rejection region. That means this is automatically alpha, or you can say probability of type 1 error if you wanted to say it that way. That would be totally fine as well. They might use those interchangeably. What about area 2? Oh, I'm going to reference my cheat sheet again. This says that for drawing, area underneath the alternative curve, which this is the red curve that this pink area is underneath, and outside the RR, so outside the rejection region is another way of saying inside the acceptance region. So outside the rejection region is inside the acceptance region. This is area 2. This is inside the acceptance region, and underneath HA, that would be beta, the probability of type 2 error. So they might list it as beta, or they might list it as probability of type 2 error. I didn't actually use the word error over here, did I? Error. Okay. What is area 3? Area 3 is all of this. What would this be according to my drawing? Well, this is underneath my HA curve. Notice it's underneath the red curve. And it's inside the rejection region because, again, the rejection region is pointing this way. That is power according to my cheat sheet. So we call that power. You can also say correct rejection. Correct rejection. What about area 4? Area 4, that's this over here. I don't have a name for it. Notice that I only have 1, 2, 3 different names, alpha, beta, and power. So what's the remaining one? The last one doesn't have a name, doesn't have a fancy name. It's just called correct acceptance. So we'll say correct acceptance of the null hypothesis. You could say something like, I don't know, what did you say? You could say.
You said probability HO will be accepted.
Yeah, okay. There we go. Will
Correct,
be accepted. So notice correctly accepted. Good point. So these are just, again, interchangeable. Correct acceptance of the null hypothesis. I mean, I said the word correct here and here. Null hypothesis was said here and here. The word accept was here and here. And technically, it is a probability. Each area shaded represents a probability. So I guess technically the word probability would need to be included. But again, you'll probably find the answer because it will be the only one that has correct acceptance of the null hypothesis. Okay, we've got that out of the way. That's pretty much what this question is going to be asking. Of course, it won't ask it in quite this way. Again, they'll just slap a graph up here, and your job is to fill in the names of the half lines and the intervals, and then fill in the names of the areas, and that will be it. All right, we'll delete all this. I don't think we need this anymore. In this problem, what is the shape of the rejection probability curve? Rejection probability curves are shaped different ways. Again, we talked about this yesterday in the session 3 practice session. We've got 3 possibilities, 1, 2, and 3. I'm going to go down a size here, a couple sizes. The rejection probability curve looks like this if it's left-tailed, like this if it's right-tailed, and like this if it's two-tailed. So let's make it look more like, there we go. So these are what the shapes of the different probability rejection curves are going to be asked about. And it's usually a multiple choice question where is it look like this? Does it look like this? Or does it look like this? So when this question came up on the Canvas exam, I'm sure it just says, You get 1, 2, 3 answer choices. You ask yourself, what was the direction of your hypothesis test? Remember, this was mu less than, nope, sorry, greater than or equal to 37, and the alternative was mu less than or equal, or just less than 37. So this was a left-tailed test, and so your answer would be this guy. That would be the shape of your rejection probability curve. Okay, moving on to p-value. P-value, I'm going to go scroll down to this section of the cheat sheet. Find the p-value. Let's go to step 1. Compute the z-score or t-score. Use the tree to determine whether or not it's z or t. We know this is a z distribution. We said that earlier. This is a continuation of a very long problem where we said at the very beginning of the session that this was a z distribution. So we're going to be using the z. The way we compute z, this is a one sample mean question. We're not going to do any of these. The p-value question usually happens on the one sample mean, but make sure you identify whether this is a 2 mean question versus a 1 prop question versus a 2 prop question. In our case, it's a 1 mean question, so we need to find the z value. Z equals x bar was given to us. What if the sample mean, down here, sample mean x bar is 33.5, or 35.5 rather, 35.5. Go back to the cheat sheet, minus h null value. H null value is that 37, divided by standard deviation. Don't forget standard deviation was, I believe, 8. And in our sample size was 64. So we're just going to keep using those same numbers from before. 8 over square root of 64. That's our z-score value. This is going to be negative 1.5. Go on to step 2. A lot of people say, Andy, what do I do now? I don't know what to do. Well, we just did step 1. So what comes after step 1? And you're like, I think step 2. Yep, good. You got the counting part right. So step 2 comes next. Compute the p-value using these formulas. If it's z distribution, you do something different than if it's t distribution, but this is still z. We're still using the z distribution. Was our test left-tailed, right-tailed, or two-tailed? It was a left-tailed test, as evidenced by this left-hand sign here. So we're going to be doing negative 100, comma, our z-score. So I'm going to do normal CDF, negative 100, comma, negative 1.5, and I have my p-value of 0.0668. And that's your p-value, pretty easy. If it's a two-tailed test, make sure you pay attention to this instruction. If we had a two-tailed test, so let's just briefly pretend this had said equals and this had said not equals, you would have done both of these calculations and then doubled whichever one was smaller. That would have been your p-value. So bear that in mind anytime you encounter a two-tailed test and you're asked to find a p-value. You're not being asked to draw a conclusion here, so don't bother doing any of that. We're just going to skip down to the next part. Above, we use a critical value of 35, but now we need a new critical value. So the critical value of 35 that was given to us before is now gone. We don't want it anymore. We're instead going to use a specific value of alpha. We have alpha equals 0.01, and that is going to help dictate our critical value. So let's go ahead and do that. All that stuff, finding the value that corresponds to the critical value that corresponds to a given value of alpha is the rejection region method. And we're going to look back up in our one mean section. Here's find the rejection region. Will we use Z or T? Let's just go through the steps. I'll label them off. Step 1 is we're using Z. We already know that. Again, continuing the long-standing practice for this one particular problem, we're going to be using Z. We need to get that Z value. That will depend on if our test is left, right, or two-tailed. And by the way, brief aside, if you're doing a confidence interval, don't use these steps. I can't tell you how many people go through looking through these steps and say, Andy, I don't know what tail my test is because I don't see it. Well, and I say, well, were you asked to find a rejection region or were you asked to find a confidence interval? And people are like, oh crap, they told me to ask to find a confidence interval. So don't look at these steps. Look at these steps if you're being asked to find a confidence interval. So there's so many people they're banging their head against the wall because they're looking at these steps when they should be looking at these. So make sure you're paying attention to the right set of steps when being asked to find a confidence interval versus a rejection region. We're doing rejection region. And in this situation, I'm going to go erase what I mangled all these equalities or inequalities. So I'm going to go fix these real quick. This was, sorry if this gets repetitive, a left-tailed test because we have a less than sign here. Left-tailed test. So we're going to do inverse norm of alpha. We'll do inverse norm of 0.01, which if I had to guess, I think is not 2, but negative 2.326. Let me double check. Inverse norm, negative, or not negative, 0.01, negative 2.326. Okay, step 3. We need to find the critical value. So we're going to use the formula here and plug in the things we know other than CV. After all, CV is the thing we're trying to solve for. So we have negative 2.326. CV we don't know. CV is the thing we're trying to find. The H null value was 37. Sigma is 8 square root of 64, and our job is just to solve for CV. So we get negative 2.326 plus 37, and I get a critical value of 34.674. We can stop here. We don't need to go on to step 4 or step 5 because the question merely asked, calculate the critical value. Do I need step 4 of setting up a rejection region and drawing a conclusion? No, I found the critical value. I'm done. A lot of people think that because I've given you 5 steps, you need to do all 5 steps. Not always. It depends on what you're being asked for. If you're only being asked to get as far as the critical value, then stop here. Don't keep going on to step 4 and step 5 if all you were asked to do is find the critical value. So we're done with that as well. Last question of this group is we want to find the minimum sample size. We see that phrase quite a bit, and that freaks us out. We're like, oh, wait a second, that should set off alarm bells. We don't want a minimum sample size page. I'm going to scroll down a bit. There's our minimum sample size. We've got a couple different types of minimum sample size questions. For those of you who have received, I actually sent out an updated document that has a 2 proportion example and how to do that. But for now, we have minimum sample size for confidence interval, and we have minimum sample size to control alpha and beta. This is not the one we want right now. We do not want controlling the width of a confidence interval. We're trying to control alpha and beta. How do I know I'm trying to control alpha and beta? Well, they said they want the type 1 error, the probability, to be 0.01. That's alpha. And they also said they want power to be 0.95. Well, power is also known as 1 minus beta. So we're also trying to control beta at 0.05. So this, the fact that we've mentioned alpha and we've kind of in some roundabout way mentioned beta, I'm going to use this part of the minimum sample size formula. In fact, all I really want is this guy. So I'm going to use that in just a second. A lot of people will use some sort of silliness to put n here. We already know, and it's be like, oh, we already know n to be 64. No, n's gone now. We don't know n anymore. N is the new value we're trying to find. So we don't know that. We at least know sigma. That is still 8. We need to find z alpha and z beta, so I'm going to leave some room for them here. We're going to square this guy, and we're going to divide by the difference in the values of the means. What are the different means? We got mu null and mu alpha. Well, we're going to provide to you 2 different means. One of them was 34. What does the other mean? This is the alternative mean. What does the other mean? Well, as you can probably guess, mu null is the one that corresponds to the null hypothesis. If you go way, way back up to the beginning, null hypothesis was at 37 up here. So 37 is our mu null. So the last thing we have to get is that z alpha minus z beta quantity. And how do we figure that out? Well, cheat sheet time. If the test is left-tailed, which ours is, we're going to do inverse norm of alpha. So inverse norm of, was that still 0.01? I believe it was. Inverse norm of 0.01. That's going to be, where's my cursor? I lost it. There he is. It's going to be negative 2.326 minus z beta. How do I get z beta? You can either use inverse norm of 1 minus beta, or if you're given power, you can use inverse norm power. So whichever they give you, in our case, we were given power. So we're going to put 0.95 in for power here. If I do inverse norm of 0.95, I get 1.645. So I'm going to put that, lost my cursor again. It's hard to see on Paint. 1.645. So we have 8 times negative 2.326 minus 1.645 divided by 37 minus 34, which is just 3. And then I'm going to square that result, and then I round up. If I do that, I get a sample size of 113. I got 112.1, but of course with minimum sample size questions, we always round our answer up. So I got 113, and that's all there is to it for that question. So we spent a fair amount of time on that question. We're done drawing. We're done with this giant group 2 question. We're going to move on to group 3.
Quick follow-up before we
go for it.
So in the cheat sheet formula, you have the null hypothesis mu minus the alternative hypothesis mu, but we use 34. Is that because the question gives us like the new alternative hypothesis?
Yes, it says, well, so don't think, so this is a mistake some people make, is that they think the null hypothesis value is 37 and the alternative value is also 37. And someone actually said that in the group, like, well, how does this work? Because if you do 37 minus 37, then you're going to get 0 down below, right? So if I put 37 here and 37 here, well, we get one of those divide by 0 answers, and that's a big no-no, right? So where do we get that alternate value? That is found given in the question. So this is where they say they want power to be 0.95 when mu is 34. So that one has to be mentioned to you. If they don't mention 2 values of mu, it's just because one of the values of mu is your original null hypothesis value, which was stated way back up here, your null hypothesis of 37. So usually they state both values of mu, but if they only stating one, they're probably telling you what the alternative one is, and you have to think back to what your hypotheses were to recall what your mu null value was. Good?
All right. Yes, thank you.
Cool. All right, let's get rid of this entire page, and we'll start from scratch. Oops. And we have another question. This is usually has several one mean questions right in a row. But this time we're going to be using, or we're saying something different about whether we use the t distribution rather than we use the z distribution using CLT. So let's start with the first question. It says calculate the 95% or the 90% confidence interval for the population mean. Cool. I'm going to jump before I actually jump to my cheat sheet. I'm going to write down some numbers that they give to us. They say approximate the normal. And again, I'm pretty good at spotting that, but make sure you read it for yourself. There it is right here. Starting salaries are approximately normally distributed. We then have standard deviation, we'll say sigma. We'll say standard deviation equals 10. How do I know this is the population standard deviation as opposed to the sample standard deviation? Well, when they say it is known, it has this distribution with a standard deviation of 10, we're not saying from a sample. And in fact, it is the next sentence that begins in a random sample of 31. So we're referring to the standard deviation from the random sample when we get to this sentence. But here, this is telling us that we know the standard deviation for the population is 10. When we get to the random sample, we get 31 graduating economics majors, the mean starting salary in the sample, so that's why I'm using X bar, not mu, 51.8, and the standard deviation of starting salaries was 12. This is in the sample, so I'm using a lowercase s rather than a sigma. Question 1, calculate the 90% confidence interval for the population mean. Of course, they could ask, what is the basis of the population? What is the distribution for the basis of this confidence interval? So let's go ahead and get those out of the way right now. The first question of this would be, what's the population? This is a normal population. Remember, this is as opposed to general because we were told it was approximately normal in the question, right? This is not a Bernoulli question. This is not a Bernoulli population because that would be for if it was a proportion. This is not a proportion. What about the distribution we're going to use? Well, it's a normal population or approximately normal with a known standard deviation or no standard deviation. So we're going to use our z distribution. Again, of course, you could write it as this: x bar minus mu over sigma over root n is distributed normal 0, 1. We will see later on how this changes in the problem because we're at some point going to use the t distribution, but we'll talk more about that in a minute. Let's go on to actually making these aren't even questions they asked you. So I'm putting these as example questions, but they weren't asked for this particular problem. So these are just little bonus questions, but I don't want to assign them a number. Let's do the actual number 1 in this group, which says create the 90% confidence interval for the population mean. So cheat sheet, scroll up to 1 mean. We want the confidence interval here. Will we use Z or T? We've already established that we'll be using Z, so that one's out of the way. Knocked that out. We need inverse norm 1 plus confidence level divided by 2. So I'll do inverse norm of 1 plus 0.9 divided by 2. Make sure you use parentheses accordingly because if you tell, I've seen too many people make this mistake. Inverse norm. They type it into their calculator in such a way that this is what the calculator is reading. 0.9 divided by 2. I do not want you to take the confidence level and divide only that by 2. I want you to take 1 plus the confidence level and divide that by 2. Notice that the 1 is also sitting in the numerator. So make sure you're using parentheses in a way that your calculator understands that 1 is the numerator. I can't tell you how many tears have been cried because you're like, oh no, I screwed up and didn't correctly list my confidence interval or in my inverse norm. So don't screw that up. I'd hate for you to lose silly points like that. All right. I don't know why I took the time to erase all that, but there we go. So if I do inverse norm of that, I get 1 point, I'll say z equals 1.645. Step 3 is construct the interval. All right, cool. We have x bar, which was given to be 51.8 minus 1.645 times our population standard deviation. We're going to use sigma here. 12, oops, I said 12, I meant 10. 10 over square root of 31 is less than mu is less than, same exact thing. In fact, I'm just going to copy this and paste it. The perks of not working in the Zoom whiteboard is that this allows me to copy and paste pretty cleanly. Oops, I don't want to cut. I do want to paste though. I'm running out of room. Let's move this over. Boom. Boom. Now all I have to do is change this minus here to a plus. And that's my confidence interval. I'm not even going to crank out the numbers. For the purposes of continuing on and moving on through all these questions, you can type this into a calculator yourself and get the actual number. But, oh, do we have to draw a conclusion? We do. Okay, great. So we do need the values because we're about to test the hypothesis test. So 51.8 minus 1.645 times 10 over square root of 31. Let's do the same thing plus. When I do that, here are my values. I get 48.845 is less than mu is less than 54.75. Oops, 0.755. Okay, so this is our confidence interval. Sometimes she writes it like this, puts a C here and then parentheses, and then says this is a 90% confidence interval. So you might see her write it in this awkward way. I just like, the way I see it is like, just give me the interval. I don't need all this extra 0.90. This is the C, the parentheses. This is an interval, right? Oop, this is an interval, right? So I'm happy with that. Now we have to draw a conclusion because that is the next part. Question 2 says, what is the conclusion of the test? If we're going to test the hypothesis test, mu equals, I should say H null mu equals 50 versus HA, mu not equal to 50. How do I do that test? Well, this is what the cheat sheet says. If the null hypothesis value is in the confidence interval, then accept the null hypothesis. If the null hypothesis value is not in the confidence interval, then reject. Well, our null hypothesis value is 50. 50 is between 40, 48, and 54. So with that in mind, we are going to accept the null hypothesis. Okay. Let's see what the next question has to ask. Which of the following describes how to use a p-value? You can kind of use what my cheat sheet says, the p-value, draw a conclusion. If the p is low, reject the ho. Or more formally, if the p-value is lower than alpha, then accept the null hypothesis. She might say if the p-value is lower than the significance level, which again, alpha is the significance level, then reject the null hypothesis. That's just a theory question. Next question says, suppose the economists wanted to find a more precise estimate of the population mean. They want the length of the confidence interval to be 3 or less. What is the minimum sample size? We have another minimum sample size question on our hands. This is one where we're trying to control the length of the width of the confidence interval. Be careful here is that I use something slightly different than what your professor does in terms of how I use this formula. Some professors use length of their interval, whereas I use desired margin of error. So we'll have to make a small tweak to our formula, at least when we get there in a minute. So our z-score, when we go ahead and do this minimum sample size question, I guess this is question 4. Question 3 was the theory question. So we'll say, where's my tool? There we go. 3, it's just theory question. What's a p-value? Question 4 is on this sample size. So n equals, it is z times standard deviation over margin of error. What I say is desired margin of error, all squared. The z value is still the same old z value from before. It is the 1.645. The sigma value is, as it was before, is still the same old 10. The last thing is our MOE, margin of error. Be careful. Your professor does not say margin of error. Your professor tends to say the length or the width of the confidence interval, for which the margin of error is half that value. So huge important note. You can write it down if you want. Desired margin of error equals half the length of the confidence interval. Okay, so it's an important note to take down. When you use my cheat sheet, if you take 3 and you put it here, you screwed up. I don't want the desired margin of error to be 3. I want the length to be 3. Therefore, I want the margin of error to be 1.5. So I'm going to put 1.5 here. Crank this out. Make sure you round up when you do. 1.645 times 10 divided by 1.5 squared gives me 120.26. But of course, we always round up for a minimum sample size question. So we get 121. Any questions on that? Okay.
All good.
Cool. Great. Next question says, is a continuation of doing a new 90% confidence interval, but this time we don't know the population variance. So remember how we said the population variance was 10 before? Let's say it's unknown. We don't know it anymore, which means we've got to do a couple things differently. Now we're going to rely on the sample standard deviation. But moreover, our population is no longer, or our distribution can no longer be used with the z distribution. I have to change this up now. So this guy's gone. I have to use the, not t distribution, but I'm going to be using s here. Because I'm using s, because I don't know the population standard deviation, I'm now using the t distribution with n minus 1 degrees of freedom. So you'll see this instead. Oh, and by the way, I should change this to be not a z anymore. We're not using the z because we no longer know the population standard deviation. This has been thrown away. So we got to do a couple things here to recalculate our 90% confidence interval. The first of which is to go back up here and recalculate the value of t. So for the confidence interval, we're now going to use not inverse norm, but inverse t of 1 plus our confidence level divided by 2. So we're going to do second distor, inverse t. This gives me 1 plus 0.9 divided by 2, comma, degrees of freedom. Degrees of freedom is your sample size minus 1. So if we have 31 people, that means our degrees of freedom is 30. So we'll say inverse t of 1 plus 1 point, or 0.95, 1 plus 0.9, which is 1.9 divided by 2 is 0.95, comma 30. I get a t-score. Where's my cursor? I've lost it again. It's hard to find. Okay, there it is. T equals 1.697. So that's going to change here. Rather than 1.645, I'm going to be using 1.697. Furthermore, I'm no longer using the population standard deviation of 10. I'm using the sample standard deviation of 12. So this guy copies and goes over here. And that's what my confidence interval looks like this time. We don't need to calculate the numbers because we're not being asked to conduct a hypothesis test, so I'll let you calculate the numbers on your own. That would be, I guess, question 5. That's a 5, trust me. It's really ugly looking 5. That's a 5. Okay, 5. The follow-up question is one more time. Now we're going to assume that we can't assume they're approximately normal. So not only do we lose the population standard deviation from before, but now we're losing the fact that it's known to be approximately normal. Well, guess what? We can probably still use, it's weird because it's just barely large enough. We can use the central limit theorem when we have a sample size large enough, which counts as about 30 or bigger, and we just barely meet that threshold. So we will be using the central limit theorem to say we can go back to using the z distribution. One thing, however, is that we're no longer looking at a normal population. We are now using a general population because no longer are we told it's approximately normal. So if you're asked again, hey, what population is this? You wouldn't say this is a normal population because we lost that fact. We lost the fact that it was approximately normal. That part is gone. So now we're referring to a general population. And because of that, we can use, what do they want us to use for the population standard deviation? I guess we're getting rid of that as well. So we're going to go back and still use S. We're going to say x bar minus mu over standard deviation over square root of n. We're going back to normal 0, 1 this time. And who says we can do that? The central limit theorem says we can because we have a large enough sample size. Even though the original population was not a normally distributed. The cool thing about that is that it really doesn't change too much of the original confidence interval. So I'm going to undo quite a bit here. If you recall, this was our original confidence interval, right? Because we're going back and using the z distribution, now we're using z, and we don't need to change the z value. However, there is one thing we do need to change. Victoria, do you know what that is? What thing do we need to change?
Is it the t or the s?
It's not the. It's the s. It's the standard deviation. So we will continue to use the z distribution because the central limit theorem says we can. But we got rid of the population standard deviation from before, so we're going to continue using 12 as our sample standard deviation. It's unknown whether or not. I'm assuming that we're not going to go back to using the fact that sigma was 10 like we did for the very first problem because they told us to forget about that way back in question 5. So. Right. Unless they again tell you somewhere in question 6, this is now question 6, by the way. Unless they tell you here in question 6 to say, okay, don't assume they're normally distributed, but let's go back and use the population standard deviation of 10, then I would continue to use 10. But because they told us to forget about that in question 5, I'm going to go back and use the 12 that they gave us secondly. Okay. Up to now, questions have been about the population mean. Now we're talking about the variance. I think they tell us to go back. You know what's funny is she didn't tell us to do this, but I think you're supposed to be told that this is an approximately normal distribution. And since we weren't, it's okay. But one thing that she should have said is go back to assuming the population is distributed normally, or assume that economics or salaries of economics majors graduating from United States universities is approximately normal. Because otherwise you can't use, I don't think you can use the chi-square distribution, which is what we're going to use for this one variance problem. So let me get rid of everything here. I'm at least going to get rid of this stuff. We don't need this anymore. The distribution that governs the confidence intervals for one variance questions is the chi-square distribution. So we're going to say n minus 1, because this is the question about variances. N minus 1 over s squared over sigma squared is distributed chi-squared with n minus 1 degrees of freedom. So if you're asked a question about what distribution governs this type of problem, you'll say this guy right here. We want to find the 90% confidence interval. So I'm going to go to my cheat sheet, go down to one variance. And we're not doing a rejection region, we're doing a confidence interval. Step 1, it's automatically chi-squared. Cool, great, done with that. Get the two chi-square values. It says, look at the chi-square values. We want the tail values of 1 minus CL over 2 and 1 plus CL over 2 with degrees of freedom n minus 1. Well, first off, I'm going to scroll down to a table in a second, but let's go ahead and figure out what 1 plus CL over 2 and 1 minus CL over 2. So we got 1 plus, it's a 90% confidence interval, so 1 plus 0.9 over 2 and 1 minus 0.9 over 2. These are going to be 0.95 and 0.05. I believe this was a 90% confidence interval. Yes, 90% confidence interval. So I'm going to get 1 plus CL over 2 and 1 minus CL over 2. And I want to find the tail values in the chi-square table. So the nice thing is for you, I've provided a chi-square table at the very, very bottom. Just barely happens to have my degrees of freedom in it. Sample size is 30, so we want 30 degrees of freedom. We wanted 0.95. 30 degrees of freedom is 18.493. I'm going to type that. So we've got one chi-square value of 18.493, and we have another chi-square value of, corresponds to 0.05, 30 degrees of freedom, 43.773. This guy on the left is chi-square lower, because obviously it's smaller. And this guy on the left is chi-square upper, because it is bigger. That's important to note, because when I go and use my cheat sheet, or for the one variance question, when you construct your interval, chi-square upper is actually in the denominator of the left-hand side. So bear that in mind when I go and calculate this confidence interval. I'm going to have, let's do this. We're going to have n minus 1, so 31 minus 1 times s squared, which is 12 squared, over chi-square upper, 43.773, is less than sigma squared, is less than 31 minus 1 again, 12 squared again, but this time I want chi-square lower in my denominator, so that'd be 18.493. Do we have to draw a conclusion? Yes, we're doing a hypothesis test. Let me get these numbers. 30 times 144 over 43.773 gives me 98.69, and 30 times 144 over 18.493 gives me 233.60. So this is my confidence interval for the population variance. You could, by the way, be asked for confidence interval for population standard deviation. So you weren't asked for the confidence interval for the standard deviation. At least I don't think we were. Let's double check. It says population variance. But had this said standard deviation, well, you know what to do. You would square root both sides. So they could have asked, what is the confidence interval for the standard deviation? In which case, you would have just taken the square root of both of these, and this would have been just a plain old sigma rather than a sigma squared. But we weren't asked for the confidence interval for standard deviation, just the confidence interval of variance. We'll leave it just like this. And we're testing the hypothesis. H null says mu equals to 100, or not mu, sorry, not mu, but variance. So sigma squared equals 100. Against the alternative hypothesis, the population variance is different than 100. Question, does 100, our null hypothesis value, fall in the interval from 98 to 233.6? Of course it does. So with that in mind, we'll say that the H null value, the null hypothesis value of 100 is in the confidence interval. Therefore, make this bigger. Therefore, we accept the null hypothesis, period. What is the follow-up from that? Does the confidence interval you calculated for population variance lead to the same conclusion as the rejection region, and is this necessary? There's one small theory. This is a very common theory question that you can find at the very bottom of the one proportion page. So unlike the one mean, two mean, and actually this also goes for one variance and two variance type questions, The rejection region and confidence interval methods don't necessarily give the same conclusion, and this is for the one proportion case. This is a really big deal. So only for the one proportion case, and maybe also the two proportion case, I guess. I'll have to think about that for a second. But for the one proportion case, it is possible to get different conclusions using the confidence interval method versus the rejection region method. These two methods might give you different conclusions, even though they will always, always, always give the same conclusion when you're talking about one mean, two mean, one variance, and two variance questions. So one mean, two mean, one variance, and two variance questions always give the same conclusion, whether you use the confidence interval method or the rejection region method. Okay, so because of this, this is a one variance question. This question was about one variance. Does the confidence interval that you calculated for the population variance lead to the same conclusion as the rejection region method, and is this necessary? Yes, always. For these types of questions, one mean, one variance, and two variance, these questions always give the same conclusion whether you use the confidence interval method or the rejection region method, period. Cool? Okay.
Yep.
I'm going to get rid of all this. So just a common theory question that they ask at the very end, usually at the very end. Group 4, migrants through Mexico. Washington Post says, we've surveyed 1,200 Mexican adults in July 2019. One question asks, what should Mexico do with the migrants from Central America that crosses the country trying to reach the United States? In the sample, 660 answered that these migrants should be deported to their country of origin. So we've got 660 people who voted some way or another out of 1,200 asked. This will be our P bar. This is what was asked and was surveyed. This was the sample proportion. I'm guessing this is 55%. Let me double check. 660 over 1200 is 0.55. Okay, so that's P bar. We are testing some hypothesis. And by the way, I'll keep our sample size as 1200. We're testing some hypothesis. H null. Test null hypothesis that H null P is 0.6 against the alternative P is not equal to 0.6. And we're going to use the rejection region method. Yes, using the rejection region approach. We need one last thing, which is the value of alpha. They say alpha equals 0.1. So alpha equals 0.1. We are going to follow the rejection region steps on the one proportion page. It's just a matter of identifying the type of question, making sure you have all the numbers, and making sure you go through and follow the steps that are associated with this type of problem. So this is a one prop question. I probably should say what group this is as well in case we missed it. This is group 4 now, I believe. Group 4. Question 1, rejection region approach. Step 1, is this a left-tailed, right-tailed? Oh, so it's automatically Z by CLT, so I don't even think about that. I don't even think about it as being a step, but it's something you need to check for one mean and two mean type questions. For a one proportion question, it's automatically Z. So step 2 is to get Z, and that depends on whether your test is left, right, or two-tailed. This is a two-tailed test. And so because of that, we need both plus and minus inverse norm alpha over 2. So we do inverse norm 0.1 divided by 2. My Z values will be negative 1.645 and positive 1.645. We need both of these. Step 3, plug the values of Z, P, and N into this formula here and solve for CV. What is P here? P is the H null value. So remember that when we go to set up this Z. We're going to have to set up two equations. Negative 1.645 equals CV we don't know. P is the H null value, so that's 0.6 over square root of 0.6 times 1 minus 0.6 divided by 1200. And if I set this up and solve for CV, 0.645 times square root, make sure you're being very, very, very meticulous about how you type this into your calculator. I get a lot of people who mess this up when they type it in wrong. 1 CV is 0.5767. And so I imagine the other critical value is 0.6233. We call the smaller one CV1. We call the bigger one CV2. And those are your two critical values. Let me double check that.
Yeah, that's correct.
Okay, cool.
Quick follow-up before we move on.
Yeah.
So at the top you put P bar, but we're using P in the formula?
Yes. We might end up using P bar when it comes down to drawing a conclusion. So that might be relevant when we do draw a conclusion. It doesn't tell us to draw. Oh, it does say just test the hypothesis. Or actually, you know what's interesting about this is the way this question is worded doesn't tell us whether we're going to end up finding critical values or whether we're going to say accept or reject. I don't know what the question was on Canvas, but here's what they could ask you. They could say, what are the critical values? That's a very common question. So, and you get 2 blanks. So you get 1 blank for if it's a, you'll say like if list CV1, or just list CV if the test is left or right-tailed. And then the next, oh man, I didn't want to do that. I clicked off of it. Oh well. And then the second blank is list CV2, or say NA, type NA if the test is left or right-tailed. So in our case, what I would imagine that the way she tests you on this question is just has you list what the critical values are. So we'll put 0.5. Our answer would be make sure we round to the appropriate number of decimal places. And for one proportion question, that's usually 4 decimals. And then for CV2, we put 0.6233, and that goes in our second blank. If this had been a left-tailed or right-tailed test, though, of course, we would have just said NA for that second blank. We've probably seen this once or twice before on some quizzes. We won't use P bar yet. We might not even use it at all. If they ask us, draw a conclusion, do you accept or reject? Well, this is where P bar will come in. So let's continue with step 4, which would be to say, set up our rejection region. This was a 2-tailed test, so our rejection region is this guy. P hat or P bar, make sure you leave P bar as a variable. P bar less than 0.5767, or P bar greater than 0.6233. So we've set up our rejection region. Let's do step 5 and draw a conclusion. Are we going to accept or reject? Well, let's look at P bar. Does P bar, which is this 0.55 value, satisfy this value, or sorry, this inequality or this inequality? Is 0.55 less than 0.576? Yes, it is. Doesn't need to satisfy both. Hell, I don't even know how it could possibly satisfy both. What kind of number would be less than 0.57 and also be greater than 0.62? It's not possible. So you're looking for a value that satisfies one of these inequalities, and if you do, you end up rejecting. So you say that because P bar equals 0.55, let's say 0.55, satisfies an inequality in the rejection region, we reject the null hypothesis. Or you might see something like reject H null. That might just simply be the answer. Whether they ask for critical values or for you to accept or reject will depend on the question. Okay.
Perfect. Yeah.
Let's continue. I think the one of the confidence interval, right? The next one says, what is the confidence interval? I'm just going to tell you to reference this formula. Notice that one key difference between this guy and this guy is that when I go to use this wacky square root formula, I'm going to actually write it out because I don't want you guys to mess this up. I need P bar. P bar comes first. So 0.55 minus Z, which is going to be 1.645, I would imagine, 1.645, because it corresponds to a 95% or a 90% confidence interval, which this is, times square root of not P, but they want P hat or P bar. So that's actually going to be a little different than what we saw here, right? Over here we saw 0.6 and 1 minus 0.6. We're going to use 0.55 and 1 minus 0.55. So this is one of the rare instances where the formulas for the confidence interval and the formulas for the rejection region method don't really match up quite like you would expect them to, at least between the confidence interval and rejection region methods. So that's just something to keep in mind for the one prop result, is that when you go to do a confidence interval, you're not quite using the same value of P inside that giant nasty square root that we did when we did the rejection region. And then we'll continue putting less than, P is less than, same thing, but instead of, I'm going to make this smaller. But instead of a minus, we will put a plus here. And so that will give us the confidence interval that we're looking for. We could draw a conclusion. We could say something like, does the null hypothesis value fall in this interval? So the null hypothesis value is 0.6. I bet you, let's go figure out 0.55 minus 1.645. Oops, that's 465. 645 times square root of 0.55 times 0.45 divided by 1200. This gives me, as my lower bound, 0.526 is less than P is less than, what if I change it up and make a plus? I get 0.574. Is our null hypothesis value of 0.6 in this interval? No, it is not in the interval. And because it isn't, again, we reject the null hypothesis. Cool. The last follow-up question is, does the confidence interval method we calculated for this result, or sorry, does the confidence interval method we calculated in this question lead to the same conclusion in the hypothesis test as the rejection region? In this case, the answer is yes, because in both cases, what did we say, Victoria? In both cases, we ended up doing what to the null hypothesis?
Rejecting it.
Rejecting. Is that always going to happen? At least according to my cheat sheet, not for the one proportion case. In the one proportion case, the confidence interval methods and the rejection region methods don't necessarily give the same conclusion. So this is the one and only one instance, and again, it might be the same thing for the two proportion case. I have to revisit that.
Right.
That this conclusion will not be the same. Not necessarily be the same. It can be the same. I mean, it was in our case. Both of these questions had us reject the null hypothesis. But when the theory question gets asked about do they lead to the same conclusion necessarily, your answer is no. Cool.
Perfect.
Okay. We've got a minimum sample size question. It says how large a random sample must be taken. It doesn't actually say minimum sample size, but it says how large a random sample. So you know what's interesting is that you could say any number here and not be wrong, so long as it was big enough, because it doesn't say what is the minimum sample size. But maybe this is what's being implied by this question. How large must the sample be before you know that your margin of error or your length of your interval is 0.04? So we're going to go re-reference the smallest sample size page. This time we're doing a one proportion question though, so our formula looks a little bit different than what we did when we did a one mean question. So we're going to have z, which is 1.645 still. It's just still the inverse norm of 1 plus c over 2. It's still a 90% confidence interval, so it's still the same z-score. That hasn't changed. Square root of p bar times 1 minus p bar all over desired margin of error squared. P bar, you might think to use 0.55. After all, that was the p bar value we calculated before. But you need to pay attention to a little note that will sometimes be in this question. We want the margin of error to be, or we want the length to be 0.04, regardless of the value of the sample proportion. When you see this phrase, or if they don't tell you, unless they say something like, it is continued to be believed that the sample proportion will be 0.55, unless we see some sentence like that, and instead we see some sentence like this, we have to use p hat equals 0.5. Do not use 0.55 here. So we're going to use 0.5 here, and 1 minus 0.5 in the middle. This is a very, very common result. A lot of people end up making the mistake of pointing the p-bar value from the original question and putting that in our formula, but we do not want to do that. Because it says we want this to be true regardless of the value of our sample proportion, we have to use 0.5. And then we want our margin of error, at least according to my formula, says we want the desired margin of error down in the denominator. Again, be careful. We want the length to be 0.04. Which means we want the margin of error to be 0.02. Be very, very, very careful about that. At least if you're using my formula. So this will be our sample size. Again, as a reminder, length was 0.04, but margin of error is half that, so I'm putting 0.02 there. If I do 1.645 times the square root of that mess divided by 0.02, I get 1691.26, but you have to round that up and you get 1692. Is that good?
Perfect. Yes.
That one proportion question was pretty easy. It was only a couple parts. Rejection region, confidence interval, do a minimum sample size. And when you did the rejection region and confidence interval, did those results necessarily give you the same result? And the answer for one proportion is that no, it's not necessarily the case. You'll get the same conclusion. Moving on to group 5. Group 5. We have recent, blah, blah, blah. So this is a two-mean question because we have high diversity ranking firms and low diversity ranking firms. I'm going to go through and read all of this. We have 31 firms that have high diversity ranking. We have a mean, this is from the sample, a mean of 12 percentage points and a standard deviation of 1.4 percentage points. Here's the problem. This is from one sample, and then we have another sample of 21 firms where their mean, we'll use Y bar here, is 8 points, and their standard deviation was 1.1 points. I need to distinguish the means here with X bar and Y bar because these are two different samples. And in the same fashion, I'm actually going to distinguish the sample sizes as well. I'm going to say NX and NY. I'm going to say SX and SY. Okay, let's start. Before I even start reading more of the question, let's hop over to the two mean. Got a lot of stuff on this page, and we're going to be using question one wants some sort of rejection region method. Yeah, using the rejection region approach. So I'm going to be using the rejection region approach here in just a minute, but I first need to get a few other things. Was it stated somewhere in the question that the population was approximately normal? Yes, it was. Approximately normally distributed. So I want to make sure I write that fun fact down. They said approximately normal. What about the variance? A phrase you very often see in a two-mean question is the phrase common an unknown variance. So we saw this time common but unknown variance. So this is a population variance. So common but unknown, we'll say population variance, if you'd like to say that, be a little more precise. Common but unknown population variance. So there's a few things that need to be done. First things first is, because we know this is a approximately normal distribution, but we don't have the population variance, these two things together tell us we'll be using the t-distribution, okay? We will be using this guy, this formula here. We'll be using the t-distribution because we have an approximately normal distribution, but an unknown population variance. And we know that when we know the distribution is normal, but the population variance is unknown, we can't use the z distribution. We have to use the t-distribution. Okay. Another thing we need to do is calculate this magical value of s, which is up here in the upper right corner of my cheat sheet for two mean. We need to use this value of s whenever we see the assumed common but unknown variance. So I'm going to go ahead and get this nasty calculation. Plug in all these numbers very carefully. You have nx, that's over here. You have sx, make sure you square it, that's right here. You have ny, that's here. You have sy, that's here. We have all these values. Make sure you plug them in very carefully. I'll give you one small sanity check. I'll give you an idea how you know you got the, let's see, somewhere in the neighborhood of the right answer in a second. So we have 30 times 1.4 squared plus 20 times 1.1 squared, all divided by 31 plus 21 minus 2. 31 plus 21 minus 2, and then square root that result. I get s equals 1.288. This number should always be between these two numbers. Just bear that in mind. So I got 1.288. Good. 1.288 is between 1.4 and 1.1. If it's not, if you get something like 2.3 or something, you screwed up. 2.3 is not between 1.4 and 1.1. Or if you forgot the square root, as some people might have done, remember there's a square root here. So if you forget the square root, you get 1.66. Is 1.66 in the interval from 1.4 to 1.1? No, it is not. So you know you've screwed something up if you get a value of s that isn't between the original two standard deviations. Now that I've got that all out of the way, we can get started on creating the rejection region. So is it z or is it t? We've already established that we will be using the t distribution. Because this is a, let's see, is it a two-tailed, left-tailed, or right-tailed test? We are trying to test the hypothesis that they are the same. So the test the null hypothesis, the mean in both firms is the same. One thing to say in the null hypothesis, you could say like this. You could say that mu x is equal to mu y. You could say like this, that the operating profits in both of these companies is the same. Or you can say it like this, where you subtract the mean of y over from the right to the left. This is somewhat useful because when I ask you what the h null value is, or the null hypothesis value is, you're very likely to say 0 because that's the only number you see in that equation. Whereas if I write it the other way, you don't see a number. The alternate hypothesis says the two mean values are different. So you can say mu x not equal to mu y. But again, in keeping with the same format as I have here, I'm going to subtract the mu y over from the right to the left. So I have mu x minus mu y is not equal to 0. And so because of that, this is a two-tailed test. Two-tailed test. Hop back over to the cheat sheet. Two-tailed test, we need t. So we're going to do inverse t of alpha over 2. Oh, I always forget to do this. What is my value of alpha? Alpha is given to be 0.1. So make sure we copy the value of alpha down as well. Otherwise, you can't find your t value. So we're going to do inverse t of 0.1 divided by 2, comma, degrees of freedom. Here, degrees of freedom is your sample. There are two sample sizes added together, but then minus 2. So I'm going to get 31 plus 21 minus 2. That would be 50. If I do that, I get a t value of negative 1.676. And we also have positive 1.676. Because don't forget, this is a two-tailed test. We need both plus and minus what we get from this inverse t. So we need negative 1.675, or negative 1.676, and positive 1.676. And now we're going to go on to step 3, which is finding our critical value. So critical value, we don't know this. H null value, we do know. What is the H null value? Remember how I told you to rewrite the null hypothesis in such a way we get 0 on the right-hand side? I do this for a reason, because when I ask you what the HNO value is, you say, oh yeah, that's 0. Okay, so my HNO value is 0. We have, in our denominator, we have S, which we found moments ago, that's this guy, 1.288 times the square root of 1 over nx, nx being our sample size for the x distribution, 31, plus 1 over 21. And this needs to equal, let's start with the negative t value, negative 1.676. Negative 1.676 times 1.288 times square root of 1 over 31 plus 1 over 21. This gives me CV equals negative 0.61, we'll say negative 0.610. Okay. The nice thing about this is that for the two-tailed test, it's very often that your HNO value is 0. And so this is CV1. Without a doubt, I don't have to even bother calculating it. I know CV2 is going to be positive 0.610. Because when you go to solve for CV and you add the 0 over to the right-hand side, well, when you add 0, nothing changes. So you end up with CV2 is positive 0.610. Let's suppose that, again, what are you going to encounter on the exam? You'll get a couple of blanks, and so they'll say, what is CV1? They'll say CV1 or CV, question mark, what are those? And then the next blank will be CV2, question mark, what's that going to be? Or if you only had one critical value, then you just say NA. In our case, this was a two-tailed test. Because of the two-tailed test, we need 2 critical values. Provide the smaller critical value first. This guy would be my first answer. And this guy, because it's a two-tailed test, I have a second critical value. That would be my second answer. You might also be asked, do you reject or accept the null hypothesis? So let's set up a rejection region. Our rejection region will be of the form RR equals, open set brace, X bar minus Y bar less than, or sorry, it's two-tailed test, so this guy. X bar minus Y bar less than negative 0.610, or X bar minus Y bar greater than 0.610. My question to the audience, the only audience member there is looking at the values of X bar and Y bar, what is the difference between X bar and Y bar? X bar minus Y bar would be what here? Do I still have an audience? Maybe not right now. Okay.
Can you hear me?
Oh yeah, I hear you now.
Oh, I said 4. I guess my mic wasn't working.
No worries. Okay, so we got X bar minus Y bar, that's 4, right, exactly. And does that satisfy one of these inequalities? Is X bar minus Y bar, that value of 4, is it less than negative 6.61?
No,
No, but
it is greater than.
Exactly, but it is greater than 0.610, so we are going to reject the null hypothesis. Good?
Yes.
They're going to probably have us do it all over again. Oh no, actually no, not at all. I'm not going to do it. I'm not going to take up the time to do it, but bear in mind, you could be asked to do a confidence interval, and you would just follow the steps down here, follow them like you see down here, and you would get a confidence interval just like that. But we weren't asked to do that. They're going to quickly segue into a 2 variance question. So it said that in the problem we just did, we assumed the population variances were the same. But now we're doing a hypothesis test. It says, using the rejection region approach, test the null hypothesis that the variance of operating profit equals the variance of operating profit for the other type of firms, against the alternative that they are different. So sigma x squared is different from sigma y squared. And again, using some alpha level of 0.1. We're going to rewrite this slightly. I like writing this that we have sigma x squared over sigma y squared equals 1. Normally, we subtract when we talk about means, but when you're talking about variances, you actually divide. So we'll say sigma x squared over sigma y squared, and this is not equal to 1 because they're different. These are our hypotheses. We're using alpha equals 0.1, and we're going to scroll down to the 2 variance section of my study guide. And we're doing the rejection region approach. Cool. All right. I think we have everything we need. Step 1 says what distribution we're using. It's automatically the F distribution. Use these degrees of freedom. So we have 2 possible degrees of freedom, DF1 and DF2. And those are based on the sample sizes from the up here. DF1 corresponds to nx minus 1. So we have DF1, what's called the numerator degrees of freedom, we can say numerator degrees of freedom. Why is it numerator? Because x is in the numerator, whereas y is here in the denominator. The df numerator, or df1, is 30, while df denominator, or df2, would be 20. So I just subtracted 1 from this, subtracted 1 from this, and that gives me my degrees of freedom. Let's go on to step 2, which is a two-tailed test. So if it's a two-tailed test, find the tail value in the F table for alpha over 2. So I'm going to go down to my F table, hoping that I have the correct one. I don't think I do, actually, because this F table is, oh, we're good. This is for alpha equals 0.05. There are different alpha tables. So there's an alpha equals 0.01 table. There's an alpha equals 0.05 table. There's an alpha equals 0.10 table. Well, I think we're okay with alpha equals 0.05. Now you might be thinking, Andy, how are we good with alpha equals 0.05? After all, this says alpha equals 0.10. How can you tell me this is the okay table? Because when we go back up to the two sample, or the two variance question, we want the F table for alpha over 2. And since our alpha value is 0.10, alpha over 2 would be 0.05. So this is actually the one we want. So we're in the right table. Otherwise, I'd have to go look one up. Make sure you're paying attention to the right table, though. Alpha equals 0.05. We have 30 degrees of freedom in the numerator, 20 degrees of freedom in the denominator. I'm going to skim over until I find that value, 2.04. So F2 is 2.04. I tell you to call it 2.04 in my cheat sheet. Call this, oh, sorry, don't call it F2, call it CV2. Let's undo that a bit. CV2 is 2.04. Step 3, by the way, you only need to do step 3 if this is a two-tailed test. If it's a left-tailed or right-tailed test, you can straight up skip step 3. Only do the step if F is two-tailed, if the test is two-tailed. Find the F value in the same table, but with the degrees of freedom reversed. And once we do that, take the reciprocal of that number. That is to say, let's go back down to our table. Rather than do 30 and 20, we're going to do 20 degrees of freedom and 30 degrees of freedom. This gives me 1.93. But you don't want just 1.93. You don't just want 1.93. You want 1 over this. This will be CV1. So this will be 1 divided by 1.93 is 0.518. Okay. You might get more decimal places than I'm giving you. I don't know if this is the exact same table as the one your professor gives you. Bear in mind that I'm just using this for my calculations, for my purposes. Victoria, do you happen to know how many decimal places that she uses for her F table? Or is it 2 or is it 3?
I have it as 2.
Okay, so this table that I'm using here is fine. You can probably use this table as well. Just be wary of the fact that I think we've gotten into some hot water earlier with using tables that didn't go to enough decimal places. So to make sure to always use the tables that she provides you. That way, there's no screw up on the basis of using the wrong number of decimal places. So we have our two critical values, CV1 and CV2. What does my cheat sheet continue to say? We have our values, CV1 and CV2. Create our rejection region. So we're going to say, again, this might be a point where she asks, what are your critical values? So you say CV1 is 0.518, and your second critical value is 2.04. And she'll make sure she specifies which one she wants you to make the larger one versus the smaller one. Our rejection region will be sigma, oh, not sigma, but sx squared over sy squared is less than 0.518, or sx squared over sy squared is 2.04. That's the way we set up our rejection region. Are we have to draw a conclusion? I guess we could. Let's do that. What conclusion will we draw? Well, what is sx squared over sy squared? I'm going to take this 1.4 and 1.1 to divide one by the other and see if it. I shouldn't say equals. I should say greater than here. See if that satisfies one of the other inequalities. So 1.4 divided by 1.1, square both of those guys. I get 1.619. 1.619 is not smaller than this guy, nor is it bigger than this guy. So it doesn't satisfy either inequality in the rejection region, so accept the null hypothesis, because 1.619 doesn't satisfy either one of those inequalities. Last one wants us to calculate the 90% confidence interval for the ratio of proportion variance. So population variance is not proportion. So we're going to kind of do same thing we did before. We're just going to follow the steps. Step 1 is automatically F. Step 2, get the two F values. We did this already. We essentially did this already. It's F2 is that 2.04 value we found, right? We go to the table, we look up the table value corresponding to 1 minus CL over 2, so 1 minus 0.9. Is this 0.9? Yes. 1 minus 0.9 divided by 2, so the 0.05 table. Look up 30 degrees of freedom and 20 degrees of freedom. That gave us 2.04. But then to get the other F value, you reverse the degrees of freedom. So rather than look up 30 numerator degrees of freedom, 20 denominator degrees of freedom, we instead flip that around and find 20 as our numerator degrees of freedom and 30 as our denominator degrees of freedom. Do reciprocal of that, and sure enough, that's the same old 1 over 1.93 value we found before. Take these things, plug them into this formula here to get your confidence interval. Yeah, sure, why not? Just make sure you're paying attention here. I want 1 over F2 here on the left. So you're going to have 1 over 2.04 times 1.4 squared over 1.1 squared. I'm using Sx and Sy from my table over here. These are my Sx and Sy values. Less than sigma squared x over sigma squared y. You need to move this. Continue. Is less than 1 over, this is going to be kind of confusing. Remember, F1 is already 1 over 1.93. So you can say 1 over 1.93, and then times 1.4 squared over 1.1 squared. And that would be your confidence interval. Any questions on that?
Yes, so on your cheat sheet on step 2, when we're finding the F1 value, you didn't put like do 1 divided by that, but we do, right?
So you're saying,
On
oh,
step 2.
oh yeah. Did I screw that up?
So you flip the degrees of freedom, like you
Yeah,
reverse.
but I didn't, I'm supposed to take the reciprocal, aren't I? Whoops.
Yes. Just
That,
double checking.
that needs to be fixed. That is a correction to be made there. Find the F value in the same degrees of freedom with the, or same table with the degrees of freedom reversed, then take 1 over. I don't know why I didn't put that there. I've never noticed that. So yeah, there needs to be, between this sentence and this sentence, do 1 divided by this value. So yeah, 1 over 1.93 needs to be done before you call that value F1. Good catch.
Okay.
Sure. Okay, that is group 5 done. Group 6, group 7, group 8, and then we have to revisit group 1. Okay, group 6. Let's type group 6. Group 6. This is probably going to be the 2 prop questions. So something you should be mentally thinking about while you do these problems is, okay, what types of problem have I done already? Actually, no, this is not the 2 prop question. This is another 2 mean question. That's fine. She sometimes will ask 2 different 2 mean questions, but kind of mentally check yourself to say, okay, have I done a 1 prop question yet? I haven't seen one. I probably should be expecting one soon. Or I haven't done a 2 mean question. I should be expecting one soon. Or I've just done 2 different 2 mean questions. I shouldn't expect a third realistically. But this is a second 2 mean question. Actually, here's what I'm going to say about this. So we'll work through it. But one thing that is different here is that notice this is another 2 mean question. But it's worth noting that the phrase approximately normal is missing. With that in mind, if you recall when we did the 2 mean question, we had to do a couple things. One is we had to find this wacky S value by using this crazy square root. And we also used this thing here. The second type of 2 mean question that she sometimes likes to ask is one for which we don't actually know that it's approximately normal. And instead we have a general population. So this is a general population rather than a normal population. Again, this is all because the phrase approximately normal is missing from the question. So important thing to note. Because of that, it's going to change the way we calculate our rejection region or our confidence interval. Let's see what the full question asks though. We've got 350 commuters from the first group. We have the number of hours spent commuting was 225. And the standard deviation was 12. This is from the sample. And we have another sample, 250 commuters, where the sample mean was 208. And the number of standard deviation of that was 11. And now we want the 90% confidence interval for the difference between population mean for the two groups. So we're going to be using the z distribution. Why can we use the z distribution? Well, we're using use z distribution, because even though the population is not known to be normal, our sample sizes are large enough so that the central limit theorem says we can use the normal distribution. That's a key fact, that we can use the z distribution, because even though our population is not known to be normal, we didn't see the phrase approximately normal in the statement of the question, our sample sizes are large enough. Again, we're talking about sample sizes that are in the hundreds, 350 and 250. Our sample sizes are large enough that we can use the normal distribution. So we'll be using the z distribution here. And that means we need to find those z values. We're doing, oh, careful, I almost started looking at the steps for rejection region, but we're not being asked to find a rejection region. We're being asked to find a confidence interval, and then the 90% confidence interval at that. So we're going to do inverse norm, 1 plus 0.9 over 2. This is going to be 1.645 as our z-score. And now we just need to construct the interval. Don't use this one on the bottom. This is the one that uses t. Use the one on the top. So it's a really long formula. Bear with me. Actually, I might just type the numbers. No, we'll just draw it out. X bar, 225 minus 208 minus 1.645 times the square root of 12 squared over 350 plus 11 squared over 250 is less than mu x minus mu y is less than, I'm not going to, obviously, definitely not going to do the same thing twice. I will just copy this, paste it over here, make it smaller because I'm running out of room, and change the minus here to a plus. And that's my confidence interval. Really gross, but you're going to be expected to calculate that number out. Make sure you don't fat finger any number or anything like that. Make sure you're typing everything in correctly. That's why I might recommend going through and double checking to make sure your answer looks good. And then we want to use the confidence interval to test the null hypothesis. This looks like a one-sided confidence interval, just based on the question. Use the confidence interval you estimated above to test the null hypothesis that the mean number of hours spent increased by 18. Oh, interesting. Rather than 0. That is peculiar. I've never seen that before. This is a relatively new way in which she's ever asked a question. She has said, assume the difference between the number of hours in the two groups. Normally, actually, I'm going to ask you this question, Victoria. What does she normally state the hypotheses to be for a two mean or a two proportion question? That the difference is what?
Is 0, because they're the same.
Right, because of this, right, exactly. So very often we see this, right? But this is something new. This is not something she's ever done before. She's saying that test the null hypothesis that the difference actually isn't 0, that they're the same, but that it has changed by how much?
18.
18. So that's the magic number that goes here. And so now all I have to do is I'm going to go out, take my time calculating this out, minus 208 minus 1.645 square root of 12 squared over 350 plus 11 squared over 250. I get...
If that decreased by 18, would it have been negative 18?
Good question. It would also depend on the order in which you wrote the means, right? So this says null hypothesis, the mean number of hours spent commuting increased by 18 from 2008 to 2018. That means mu x better darn well be the 2018 group, which it is. I think that the first group is 2018, and it says as much. It says first group is 2018, second group is 2008. So this is 2018, this is 2008. So yes, it better be mu x minus mu y is equal to 18. Now you could say decreased, so there's two ways to write that. You could say mu x minus mu y equals, as you said, negative 18. Or alternatively, I could write it as mu y minus mu x equals positive 18. Or I could just swap these numbers. I could call this guy x and call this guy y. So there's lots of different ways in which you can set up your hypotheses on the basis of, one, how you order your variables in your hypothesis, whether it's mu x minus mu y or mu y minus mu x. Although I would say that mu y minus mu x is a little uncommon. We just tend to put what comes right before y, x, right? So mu y minus mu x is uncommon. What is slightly more common is that we just order these differently. Right? I know this is the 2018 group, but she might end up, even though she listed these values first, she might end up calling these values y, or the population y, and then she might end up calling these x, even though she listed these values second. Pay close attention to what she says, but because I was worried just now that I might have actually screwed that up, but she does indeed say the population mean in x, what she calls the x population, and the population mean in 2008, what she calls the y population. Pay very close attention to this, because I think I've seen at least on one occasion where your professor has, even though she listed 2018 first, in some point in the statement of the question, called them the y population and vice versa. It seems very tricky of her. Yes, I agree, but just pay close attention. Don't let that happen to you. But yeah,
Okay.
I think you're right. That had it said decreased, I think it would have been negative 18. Yeah. So
Cool.
I'm going to continue with this confidence interval. That means I need to do the recalculation, but instead change this to be a plus, and this gives me 18.56. And then how do we test a conclusion using a confidence interval method? We go to see if the null hypothesis value is in the interval. Well, since our null hypothesis value is 18 and it is in the interval, we accept the null hypothesis. Accept the null because 18 is in the interval. That's it. Cool.
Yes.
Slightly different question. It's a slightly different question just because we're using the central limit theorem, and because of that, it uses a slightly different formula for the confidence interval than when we did group 5. Okay. All right. Question 7. This is the 2-prop question. So this is group 7. This is the 2-prop question. We have a bunch of stuff here. We have 400 office workers from 2020 and 140 of those 400 telecommuted. This comes out to be 0.28, no, 0.35. And then we have another group of office workers. These are the 2023 office workers, so off in the future. 120 of these workers telecommuted. So 120 over 500, that would be 0.24. This is the time where, this is the instance I was mentioning before, this guy is the Y population, and this guy is the X population. See, it says the office workers who telecommuted in 2023, they're the X population. So everything I've labeled here is kind of messed up. I'm going to actually, not delete, but just erase these subscripts and fix them accordingly, just because I told you it could happen. This is the one of the few occasions I've seen her swap the letters on you based on the order in the question, right? Don't assume that just because it was listed first means it's the X population. Pay close attention to that. We want to create a confidence interval. Okay, easy enough. So this is a 2-proportion question, confidence interval, and I want the 90% confidence interval. She's got a kick for the 90%. Usually we see 95%, but we haven't seen that quite that much today. 90% confidence interval for the difference between telecommunicated in 2023 and 2020. So we're using this is the X population, this is the Y population. I'm just going to jump to the formula on my cheat sheet. I'm going to do a 2-proportion confidence interval. The nice thing is that it's automatically Z, so we're going to get our Z score. That's inverse norm 1 plus 0.9 over 2. We've seen this enough now by now to know this is 1.645, but always use your calculator to double and triple check to make sure you're not screwing that up. You don't have to flex on the exam like, oh, I know my Z-score is off the top of my head. Only I can do that. Inverse norm of 0.95 is indeed 1.645. Now we have to set up our interval. This formula is so long that I cannot put it in this box. I had to say, check it out below. So you have to get px hat or px bar minus py bar minus all this. So here we go. 0.24. It's almost kind of sad that I'm going to do this. I might just give up halfway through. Minus 1.645 times square root, giant square root, 0.24 times 1 minus 0.24, 0.76 if you'd like to say that. That's a 4. Over 500 plus 0.35 times 1 minus 0.35. All divided by our sample size here of 400. Less than px minus py, less than, and then I'm going to copy the same thing because I'm lazy. Copy, paste, change the minus to a plus. And whatever those numbers come out to be, great, good luck, have fun with that. I'm not going to bother cranking that number out. It's disgusting. Suppose the economist decided to test the null hypothesis using a rejection region approach. Which of the following could be a basis for that test? I'm actually going to pull up, let's see. I don't know where I have the solutions to this, but I might just skip this for now because there's different answers that could be used as a basis for this. There's a few. One of them is, let's do this. Can I click off of this? No, where can I go? Where did I put that? Give me 1 sec. I've got to find it in my email. It's a different tab. Oh, I could have just tabbed over here. No. Summer 2020 answers. I think this is them. Yeah. Where? I keep going, keep going. There it is. Okay. So, which of the following are you allowed to use as a test for this? So you're allowed to use this formula. Wait, this is for the confidence interval. So the economist says it's a theory question. It's really annoying. You can either pool them. This is called the pooled version, or you can use this. This is unusual because I thought it wasn't this one. I'm pretty sure you couldn't have used this one. I thought you had to use it had to be without p bar. If you do the confidence interval method, you have to use I'm a little surprised at this because I'm almost certain this is a typo. Let me see. Yeah. Wow, this doesn't look right.
So her explanation is at the bottom under the added question. It says the first one we can use by the CLT because we have independent large samples from 2 Bernoulli.
Yeah, but hold on 1 second. It's just a matter of whether I use p hat or p bar or not. Oh, you know what? I am confusing this. Okay. Here's what I wanted to say. Yeah, I've got it now. Okay. You can use either of these for rejection region, but and then there's another you can't use this one for confidence interval. Yeah, that's the deal. So have a look at both of these. You're allowed to use this one and this one when you do the rejection region approach. That's what it was. I had to think about it for a second. Both distributions here are allowed so long as you're doing the rejection region approach. However, if you're doing a confidence interval method, you cannot use this one. You must use this one. That's the rule. Okay. The reason you can't use this one, the second one for the confidence interval method, is because when you do this, you're assuming the population proportions are the same, but that's not necessarily true when you're doing a confidence interval. We're assuming that it's true for a null hypothesis or for a hypothesis test because that's the null hypothesis. We're assuming that px equals py. So either one of them can be used interchangeably, and both answers are accepted depending on which one you use. Now, my cheat sheet does not incorporate this because this confuses people. This p bar, this was called pooling method,
Right.
and some people, I feel like this can be confusing. So I only stick to using this method, but that doesn't mean you couldn't use this method. So when she asks a theory question about which of these distributions will work if you during the rejection region method, both of them could work. But if you're asked, which of these can I use? Which of these is the basis for my confidence interval? It is only the first guy. It is only one that is the basis for a confidence interval. You couldn't do the same thing for 2. Cool?
Yes. And so what's like the keyword that lets us know that we can use 2? Is it because px minus py is like the parameter, so therefore it would be 0, they would be the same, and then we can pool?
Right. Well, if we're testing a null hypothesis, so what's allowing us to use that second one where we could say p hat equals x plus y over nx plus ny. It's usually in a hypothesis test where we're testing to see if px equals py. And if we're doing that, when we go to say that px equals py, that's our null hypothesis, then what we're going to do is we're just going to lump everything in the same proportion, lump everything in the same fraction. And that's what we're going to say p bar is just the sum of everything that happened, all the number of successes divided by the total population. And when doing so, that's operating under the null hypothesis that px equals py.
Yeah. Okay, sweet.
Cool. Okay. Question about, we got one last question about minimum sample size. I sent out a more updated cheat sheet for minimum sample size. And in that cheat sheet, the more updated version, although I have to update it again because I screwed up my 2 variance thing, right? This needs to be changed to this as reciprocal. Whoops. Minimum sample size here has an additional category for 2 proportion. The cool thing is the 2 proportion one is pretty simple. It's oops, I want to just drag this, get rid of this. The 2 proportion one is almost the same exact formula. In fact, it is the same formula as the 1 proportion. We're going to do z times square root of p bar times 1 minus p bar over desired margin of error squared, and then round that up. Except for the fact that we have to do one small thing before we do this. This is, before rounding, double your answer, then round, okay? So if you're doing a 2 proportion minimum sample size, and this is just, again, what the updated version will say. So for a 2 prop minimum sample size, we're going to do our usual, jump through the usual hoops. I assume this is a 90% confidence interval. Yes, it is. So we still have 1.645. That's our z-score. It says, again, regardless of what the values of p bar and py bar, px bar and py bar turn out to be. That's, again, telling you that p bar is 0.5. Remember, if it says regardless of the values of p bar, then we assume p bar is 0.5. Our desired margin of error, be careful, it's not 0.06. The length needs to be 0.06. That means our desired margin of error is 0.03. We're going to square this guy. If this was a 1 proportion question, we would normally take this guy, round it up, but we're not going to round it up just yet. This gives me 751.67. Don't round up just yet. You're going to double it first to get 1503.34, and then round up. So for an answer of 1504. And this is the answer to that question. Good?
Yes.
Okay. We're going to, on our last questions for bias and MSE, I'm trying to decide whether or not I would like to go on to trying to see. One sec, gotta send a message real fast. Should I go back to question 1? Now I'll just continue trucking along with the bias and MSE, although I'm not gonna like it too much. I hate the bias MSE questions, so let's do that. There's paint. Let's share screen. So let's dive into, this is the wrong one. Okay, bias MSE. So remember, some of these are just definitions, like theta hat minus theta is sampling error. I'm just going to type that. Whereas expected value of theta hat minus theta, that's known as bias. So some of them might just be definitions. Let's see what we have here. So the bias of theta hat, which would be this value minus this value, notice that expected value of theta hat is right here. It is smaller than theta. So this is going to be a negative number. You can assign this a number if you'd like to. You can say, I'm actually going to screenshot and paste it over here. Copy this guy, paste it. If you want to, give these numbers. Let's call this 5. Let's call this 7. Let's call this 8. Okay. What would you tell me the bias is. What would you tell me expected value of theta is minus theta? Well, that would be 7 minus 8. That would clearly be a negative result. Okay. What about the sampling error? Well, sampling error isn't expected value of theta hat. It's just theta hat minus theta, and that would be 5 minus 8. So it's still negative. It's negative 3. So the answer is both negative. The bias and the sampling error are both negative, and it's just using these definitions of what sampling error and bias are. More definitions. I'm going to reference my cheat sheet. This guy, expected value of theta hat minus theta squared, that's known as MSE. Well, that's exactly what I see here. This is the definition of MSE, or mean squared error. So it could only be answer choice 2. None of these could be right. And as a follow-up, theta hat minus expected value of theta hat squared, expected value of that, lo and behold, that is variance. So that would go here for answer choice 2. How many more do we have? We've got 3 questions left, multiple choice left. We are testing a hypothesis about theta, about significance of alpha. Our estimator of theta is theta hat. We reject H null if, yikes, what is all this saying? The 1 minus alpha confidence interval overlaps with the H null value, or if the p-value is larger than alpha. No. So let's start with p-value, because p-value is simple. We reject if p-value is lower than alpha. So which answer choices could be right on that basis alone? This says p-value larger than alpha. Wrong. Looks like a green X, so I don't like that. Let's do a red X. Wrong. P-value larger than alpha. Wrong. Both of these say p-value smaller than alpha, so these could be right, but we have to narrow it down. We reject if the confidence interval does not overlap with the null hypothesis value. So this isn't new information. We know this from everything we've done so far. We reject the null hypothesis if the confidence interval does not contain the null hypothesis value. That's another way of saying the 1 minus alpha confidence interval, I should say, for theta excludes the H null value. So that would be answer choice 4. This one says you reject if the confidence interval includes the null hypothesis value, but that's when you accept. You reject when the null hypothesis value is excluded from your interval. Cool? Okay, move on to question 4. P-values are pretty simple. P-value is just this red area here. Is it? What is, wait, oh, sample value. That's confusing. P-value is actually not this. This red area is alpha. So she didn't actually say this. That's confusing. I'm going to copy this as well. Nope. This graph. So this red area, I guess plus this red area, these two guys make alpha. So these two red areas, I should do this in red, shouldn't I? Add up to alpha, our significance level. Whereas when you're trying to calculate a p-value, that's done based on some sample value. So the blue areas, I'll do that with this guy. These two blue areas add up to the p-value. And actually, bear in mind that even though we don't see it, this blue area continues on to the right beyond what we see here. So the p-value is all this stuff. It wouldn't just be between 7 and 8.5. It would be 7 and beyond and 3 and below. So all of this is a p-value. With that in mind, your answer is to the left of 3 and to the right of 7. So that's the p-value. That's really tricky. At first glance, whenever I saw this question, I've always thought, oh, okay, p-value is just the red guy. No. The critical value defines your value of alpha. So your critical value, which is what defines your rejection region and your acceptance region, this red area defines alpha. When you're trying to find a p-value, you're using a sample value and seeing where that falls on your distribution. And if it's a two-tailed test, which this is, by the way, this is a two-tailed test, you would get both the left-hand side and the right-hand side. Remember, you double whichever value is smaller, and since this guy over here is the smaller value, if you did the right-hand side, it'd be the larger value. We want this left tail we double it to get the right tail for our p-value. That one was really confusing, but now you know how to tackle that one in case you encounter it. And lastly, we are testing these guys here. Oh, this is a fun one. This is how she's testing you on one-sided common interval. So notice that I've pretty much used every single thing in this cheat sheet except for this guy right here, one-sided confidence interval. I haven't talked about this at all. So one-sided confidence intervals, the purpose of this is that one-sided confidence intervals are used to test left and right-tailed hypotheses. You cannot use a two-sided confidence interval to test a one-sided hypothesis. Notice that this is a right-tailed test. Notice this says no, alternate hypothesis is mu greater than 5. That's a right-tailed test. So because it's a right-tailed test, I cannot use answer choice 1 or 2. These are two-sided confidence intervals. I must use a one-sided confidence interval. Well, this is pretty easy. We've already identified that this is what tailed test. This is a right-tailed test. And so with that in mind, I need to use this confidence interval. Don't use this one. This is a left-tailed test confidence interval. Left-tailed test has negative infinity up to some number, whereas a right-tailed test has some number up to positive infinity. So with that in mind, it has to be answer choice 4. There's no way around it. Answer choices 1 and 2 are wrong because those are two-sided hypotheses or two-sided confidence intervals. They can only test a two-tailed test. This is a left-tailed confidence interval. The one-tailed confidence interval or one-sided confidence interval, but it would only test the left-sided hypothesis. Well, our test is right-sided or right-tailed, so we have to use the right-tailed confidence interval, which gives us this guy, which has to be answer choice 4. Okay, we've done every group except the very first group, so I want to revisit that one real quick. This is the small prop question, and this will be where we end doing all the solutions for this. Economist wants to study the impact of, we have approximately 0.8% of people paid off their credit card debt. So we're going to start with P equals 0.8. Therefore, economist wants to test the null hypothesis that with financial counseling, the person who rolls over the credit card debt will pay it off within 6 months. That probability is less than or equal to 0.8. So we've got null. I'll actually put this as null hypothesis. P is less than or equal to 0.8, whereas the alternate hypothesis is that P is greater than 0.8. It doesn't say about an alpha level. You very often won't have an alpha level with the one prop question. And by the way, this is back to group 1. We're going to use 5 decimal places. We tend to use a few more decimal places when we do this. In fact, she's even helping you out here. Say, make sure you go to more decimal places when you're calculating, and then round to 4 in your final answer. I'm not going to round to that many. I'm just going to round to 3 probably and call it a day. Suppose the sample size is 15. Let's continue with that. N equals 15. And we're going to do the rejection region. We'll reject if rejection region is x equals 15. By the way, I should talk about the population real quick. This is a Bernoulli. I didn't really mention this for the earlier questions when we did 1 prop and 2 prop, but for 1 prop, 2 prop, and small prop questions, population is Bernoulli. For 1 prop and 2 prop, the distribution is Z by central limit theorem. So you see that weird looking P bar minus P over the square root of P times 1 minus P over N, whatever is distributed normal 0, 1. But for small prop, which is the problem we're working on here, small sample proportion, the distribution is binomial. You say is X is distributed binomial in comma P, or you might even see X is distributed binomial, the whole word written out in comma P, okay? So that's what we're doing here. We have a population that is Bernoulli, and the distribution is X is binomial N and P. Make sure those are things that you have to tend to answer right off the bat, questions she asked at the very beginning of the question. All right, the very beginning of the problem. First question says, calculate the probability null hypothesis will be rejected if P is 0.8. Well, we just said rejection occurs when all 15 people pay back their loans. So we're going to do, what's the probability that all 15 people pay back their loans? This is a binomial distribution. So if I want to find the probability that all 15 people pay back their loans, well, I'm going to use binom PDF. We have 15 trials. The probability of this happening, we said use P equals 0.8. And then we said reject only if all 15 pay back their loan. So I do binom PDF 0.8, 15, 0.8. Well, I'll just tell you what the answer is. You get 0.03518. Okay, that's the answer to the first one. Then it says do the same thing for 0.8, 0.78, 0.85, and 0.9. So recalculate 15. We're going to do it all over again. Binom PDF 15, comma 0.75, comma 15. Just going to copy and paste this 3 times. But then change it. So we want this to be 8.5. We want this to be 9.0. When I do these, 0.75, raise the 15th, 0.01336, 0.08735, and then 0.9, I get 0.20589. Okay? We have to state which of these are power and let's see, which of these are type 1 error or power. This is these two type 1 error. Why are these a type 1 error? Because what did we say about P here? We rejected. These are all rejecting. These are all, what is the probability of rejecting? But we were rejecting the null hypothesis. I probably should say what we're rejecting. We're rejecting the null hypothesis. That's what we tend to say we reject. Rejecting the null hypothesis, even though the null hypothesis was true. P is less or equal to 0.8. That's true here. That's true, and that's true. Well, if we're rejecting something that's true, that seems like to be a bad idea, right? That's why it's a type 1 error. We're rejecting something that's true. Whereas these are power. Why are these power? Well, this is, again, rejecting the null hypothesis, but that's good. We're rejecting the null hypothesis when the null hypothesis is false. After all, the null hypothesis says P is less than or equal to 0.8, but here P is 0.85 or 0.90. The null hypothesis is false, so we should be rejecting. So when you reject the null hypothesis when it is indeed false, that's considered power. We're not going to draw a probability rejection curve or a rejection probability curve. We're just going to continue on to the small sample size that allows the maximum probability to be controlled at 1%. So what we're going to do is it helps to list out the possible numbers of outcomes. And right now we've got 15 different people repaying loans. And we set the rejection region at 15 and above. Well, just 15, right? And when we did this, the best possible value, the maximum probability of a type 1 error was 0.3518. This is you're basically using the value right at the cusp of the null hypothesis of 0.8. I got 0.035, but guess what? I want it to be 0.01. So I want this number to go down. We'll just say right now, this is too high. So how do we fix that? What we're going to do is we're going to increase our sample size until such a time as our alpha value goes below 0.01. How do I do that? Here's how you do it. You're just going to change your rejection rate. We're going to increase our sample size to 16 and then put the rejection region here and recalculate. So that would be, what's the probability that 16 people pay back their loan? We'll do binom PDF of 16, comma 0.8, comma 16, because now our sample size is 16, and we're rejecting if 16 people repay their loan. If I do that and do binom PDF with 16 as my value of n and my x value, and 0.8 is my probability, I get 0.28. Okay, that's still too big. I'm going to change it to 17. And if I did that, I get 0.022, still too big. I'm going to change it to 18. 0.018, still too big. I'm going to change it to 19. This is all going to be done on a calculator, so you can do this painstakingly by hand, one at a time. Now I'm doing 20. When I do 20, I get 0.011. Still slightly too big, but I bet you when I switch to 21, sure enough, when I do binom PDF with a sample size of 21 and I set my rejection region at 21, I get 0.009. And so your answer to this question, and I guess this would be probability of 21, is now minimum sample size needed is 21. Good? Okay. Yeah, go ahead.
Do we always assume that we're having the smallest rejection region?
Yes. So, right. That is correct. When you do this, you continue assuming that when you increase your sample size, your rejection region is going to continue to move with the rejection region. Or did I say the same thing twice? Your rejection region is going to continue to move with the highest value. So as we were to go up to 17, this guy would be our rejection region, and this guy would go away. And it would do that every single time. Otherwise, if actually think about the alternative. What would happen if we didn't move it? Well, then our type 1 error probability would only get bigger, right? If we just continued making our sample size bigger, but we had these values still here, we'd be just picking up more and more area as we increase our sample size, right?
Right.
So our rejection region has to move with the highest sample size. It's not the case when it's this is a right tail test, so that always has to happen. But for a left tail test, guess what? For a left tail test, it always stays where?
0.
It stays at 0. So that's something important to remember, that when you're doing a left tail test, the rejection region doesn't end up moving, but your sample size does end up getting bigger and bigger. When you have an increased sample size for a right tail test, you have to keep moving the rejection region up with the sample size. Okay, this last question says, what if, let's pretend for a moment that we had a sample size of 25. Okay, let's pretend we had 25 as our sample size. I'm gonna erase these numbers because actually, here's what I'll do. It'll be clever. This was a 25 all along. This was a 24 all along. This was a 23 all along. Great. When we want alpha, this time we want alpha to be 0.05, at least no bigger than this value. What is the rejection region we could use? So let's use 25. If I do binom PDF, let's get rid of this guy. If I do binom PDF of 25, 0.8, 25, what do I get for my value of alpha? Let me do that real quick. I get 0.00377. Is that, I'm going to have you answer these questions, kind of follow along. Is that less than 0.05?
Yes.
Yes, so we're good there. But let's keep making our rejection region bigger. Let's move it down. Let's include 24. So we're going to need to add binom PDF of sample size is still 25, but now I want the x value corresponding to 24. So this one comes out to be 0.0236, we'll say. I'm going to add that together with the 0.00377, and this gives me 0.0273. Is that still less than 0.05?
Yep.
Yep. Okay. Well, we'll do it one more time. Let's move this back one more and say use this as a rejection region. So we're going to add one more binom PDF and see if this is still less than, let's do a different color. 23. If I do that, I get 0.07. So already we're off to a bad start because 0.07 is already above our threshold. I don't even care what the rest of the numbers are. If I add this number, and this number, do I get something less than 0.05?
No.
No, so we screwed up by going as far as we did. We can only draw our rejection region to go up to here. We can only do this. With that in mind, the convention is you have to say the critical value is the first excluded number from the rejection region. So a critical value, a lot of people want to say is 24 because that's the number that separates the rejection region from the non-rejection region, but you don't do it in terms of what number is inside the rejection region. You do it on the number that's outside the rejection region. So your answer to this question would be 23. That is the critical value that you'll use, that you can use to make sure alpha is less than 0.05.
Is that because you can only describe the rejection region as a strict inequality?
Right, exactly.
23?
Exactly. So you see how it says inequality is strict. So rejection region, remember how this is how we've always done it, right? We've done x bar greater than or x bar less than, not greater than or equal to. So in the same fashion, we're going to say x greater than. I couldn't say x greater than 24 because if I said that, well, then I'm only referring to this part, right? I'm only referring to 25. So what number would I need to say here to imply these two values? Well, it would have to be 23.
Perfect.
Good?
Yes.
Okay, that concludes every single question from, yeah, I think that was all of group 1. Every single question from summer 2020. Hope you guys all found that useful. And if you have any questions, you know where to find me. Good luck, and I'll see you guys later.